Welcome to the first presentation in Unit 9. It's entitled Here's to the Chemistry, the cause of and solution to all your problems. It says everything is a miracle. It is a miracle that one does not dissolve in one's bathwater like a lump of soap. Hopefully by the end of this presentation you'll understand why you do not. So the learning goals for this particular presentation are that you become familiar with the key vocabulary regarding solutions, that you be able to express concentration and molarity, molality, and also parts per million and parts per billion, and that you be able to create a solution of known molarity in the lab. So here's what we already know. We know that you can express the number of molecules in moles, and it's a lot more useful to use moles than it is to use individual atoms or molecules because of the sheer number of them. We also know that molecules must be able to physically interact in order to react. If you have a molecule here, and a molecule here, and there's no way that they can actually get to one another, then there's no way they can react. We also know that molecules can be classified as ionic, polar covalent, or non-polar covalent based on the electronegativity difference between the bonds. So if you have something that has an electronegativity difference of 0.5 or less, we consider that to be a nonpolar bond. So here's what we learned in the lab. We learned that solvents dissolve a solute to make a solution. Okay, that's kind of an interesting way of saying this. We also know that solvents dissolve different solutes. So some things dissolve really, really well and some things do not. We also learned that one measure of concentration is molarity, which is also expressed as moles per liter. But that's just one of the expressions of concentration. So, to explore, a solution is a combination of two different substances. Generally, a solution is considered to be a homogeneous mixture, which remember means that it's the same throughout. So you're not going to, if you take a sample here and a sample here and a sample here, they're going to be identical. Okay, a solution can be physically separated. An example of it is Dr. Pepper, Kool-Aid, salt water, air. All of those things you can separate the solute without doing a chemical reaction. In other words, Dr. Pepper is not a new substance, it's a combination of sugar, water, and carbon dioxide. Kool-Aid is not a new substance, it's a combination of sugar and water. Salt water is not a new substance, it's a combination of salt and water, and so on. So solutions can be physically separated because they don't actually chemically react. Solutes is the substance that is dissolved into another. So it is the one that tends to disappear, and that's kind of not a great term for it, but it's the one that actually dissolves in the solute. So it's the substance. It can be a solid, a liquid, or a gas. For the most part, we're going to study the ones that tend to be solids or gases. So can we dissolve carbon dioxide in water to make carbonated water or some sort of soda? Can we dissolve solids in water like sugar or something like that? And they tend to disappear in the sense that you don't really see them, but they are still present in the solution. So they have to be able to mix with the solvent. Next you have the solvent, and it is the majority substance. Okay, so it's the one that there is the most of. For whenever you look at coffee, the majority substance of coffee is water. So because of that, you would consider water to be the solvent. Now the coffee bean could be the solute, the sugar could be the solute, the milk you add to it could be the solute. Solvents traditionally are generally liquids or gases. You're not going to see solid solvents at this level. Next, we have the idea that like dissolves like. So if you have a polar solvent, it will dissolve a polar or ionic solute. So for example, remember when we talk about polar things, remember you have things like water as an example of a polar thing. Now the reason why water is polar is because it has a partial negative charge and a partial positive charge. And because of those charges right there, these are called poles. And so because you have these poles, you have the attraction between positives and negatives. That is what allows like substances, like polar solutes, to dissolve in a polar solvent. So for example, if we have something like NaCl, NaCl is an ionic substance, which means it has a positive charge and a negative charge. The reason why salt will dissolve in water is because it has these negative charges that are attracted to the positive end, and these positive charges which are attracted to the negative end. That's what allows it to dissolve in the particular substance. It becomes part of the solution where it's arranged around it. So polar solvents, like water, will dissolve polar and ionic solutes because they are both charged. On the other hand, nonpolar solvents will dissolve nonpolar solutes. So you can't take something like salt and dissolve it in gasoline. It won't work. You can't take something like ether and dissolve it in water. It won't work. Like dissolves like, and by that, remember, we're talking about the polarity of the solute and the polarity of the solvent. So if we look at the solubility chart again, we said that everything is soluble to some degree. Whenever we say something is insoluble, we means that it has a very, very, very low solubility. Okay, you can pretty much take anything and dissolve a little bit of it. But what I mean by a little bit is you can dissolve like 4 times 10 to the minus 15th of, say, lead iodide into a solution. So technically you can dissolve some of it in, even though it's classified as insoluble. Okay, so really when we're talking about solubility, we're saying to what degree can you dissolve it in water. Water is often called the universal solvent. Why is this the case, and why is it true? And it's one of those things that should be not true, okay? Because the thing about water is water will dissolve a lot of things. Anything that is polar or ionic will be dissolved by water. And that's a lot of stuff. Even things that are slightly polar. If it's slightly polar, water will dissolve it. So that's the reason why water is considered to be the universal solvent, because it can dissolve so many things. However, it's not really universal, and the reason why it's not universal is if you have something that looks like this, it will not dissolve in water because it has no polarity whatsoever. The lack of polarity means that it can actually dissolve into water. So water is a great solvent, but it's not a universal solvent. Next, it says the nutritional label for a soft drink is shown below. Name the solutes and solvents. So the first thing we need to do whenever we're looking for the solvent is we have to identify the largest one and what's there the most of. And when you look at what there's the most of, it's the first ingredient, carbonated water. Now the problem with carbonated water as our solvent is it actually already has something dissolved in it. Carbonated water is water and CO2. Carbon dioxide. So we need to pick the solvent based on that. So the first thing we're going to do is we're going to say water is the solvent. We're going to say that we dissolve water or CO2 in water. So we're going to classify water as the solvent. The reason why? There's more water than there is CO2. The second thing we need to do is we need to start to list some of the solutes. So the first solute that I'm going to list is going to be CO2. But then you could also add sucrose, which is just another name for sugar. You could also add caramel color, whatever that is. You could add phosphoric acid, which is H3PO4. You could add natural flavors, whatever that is, and you could also add caffeine. So water is the solvent, and everything else that's dissolved in it is considered to be a solute. Next, it says one particular brand of antifreeze consists of 50% water and 50% ethylene glycol. Name the solute and the solvent for this particular solution. So this is a tricky one because there really is no great answer. Generally, the solvent is the one that there's more of. But in this case, you don't know which one there's more of because it's a 50-50 mix. If that's the case, we tend to identify water as the solvent just because it's generally considered the universal solvent. And then we would say ethylene glycol would be the solute. But in actuality, since it's a 50-50 mix, it wouldn't matter which one you identified as the solute and which one you identified as the solvent. Okay, next, we need to talk about concentration. Concentration is thought of as the density of the material. In other words, how much is there per unit of volume. So for example, if you were to look right here, these two beakers have the exact same number of particles. But because this one has a much smaller volume, it's got a greater solute to solvent ratio. So because of this, the concentration in a small beaker is much larger than the concentration in the bigger beaker, even though the number of particles are the same. It has to do with the ratio of the number of solute particles per solvent particles. So we tend to express concentration for the most part in molarity. Molarity is an expression of the moles of solute divided by the liters of solution. So this tends to be what we use most of the time. Now, whenever you do this, molarity is expressed as a capital M. That's what the unit stands for. That capital M stands for moles per liter. Now, it is a calculated quantity. You should be familiar with moles and moles and volume and liters. You should be familiar with those already. Now, molarity is not the only value for concentration. In fact, there are several other values for concentration, including molality, which is a common expression for concentration. Molality is very, very similar to molarity. Whenever you look at molarity and molality, the only difference is kilograms of solvent as opposed to liters of solvent. That's the only difference between the two. Now, molality is also very, very useful. It is expressed as a lowercase m, and it tends to be kind of an italicized or a cursive m as opposed to just kind of a regular print m. So it tends to be kind of a cursive or a tail m just to indicate that it's molality as opposed to mass or something else. So molality is really important because it's expressed in kilograms of solvent. Molality is generally used when when you're doing an experiment where the volume can change. So for example, if you are heating water in your investigation, the volume of that water will change as you heat it up. So you don't want to express concentration in molarity because the molarity changes as the volume changes. So you would express it in molality. So molality is really useful when you're looking at things like boiling point or freezing point or something along those lines. Molality becomes really important. Okay, we also have parts per million and parts per billion. So a lot of times we refer to pollutants in parts per million and parts per billion, particularly when we're talking about our water supply. It says, okay, well, out of the water particles that are there, or the mass, how many of them are lead, or how many of them are toluene, or how many of them are benzene? Now, whenever you're doing this, the parts per million is just a mass ratio. So you take the mass of what you're looking for, like lead, divided by the mass of water, and then you multiply it by either a million or a billion. This is parts per million because you multiply it by a million. If it was parts per billion, you would multiply by 10 to the ninth. It is really important that you be able to express values in concentration. So let's look at this first one. This first one says a student dissolves 0.25 moles of sodium chloride in 325 mils of solution. I want to know what the molarity is. So the first thing that I do is I realize I want to find the molarity. So I'm going to write m equals question mark. I know that this is the number of moles, so that's my n value, 0.25 moles of sodium chloride. And I also know that I have 325 mils of solution. Now you should know that the formula for molarity is equal to the number of moles divided by the volume, where the volume is expressed in liters. So we can't leave this in milliliters. We have to convert it to liters. And by doing that, we divide both sides by, we divide by 1,000, and that gives us 0.325 liters. Now we can go ahead and plug into our formula, and our formula is molarity is equal to 0.25 divided by 0.325, and whenever you plug this into your calculator, you should get a number around 0.769. Now when you do that, that's not the right number of significant figures. If you were to look, the smallest number of significant figures that I have right there is 2. So the best answer that I would have here would be 0.77 would be my molarity of NaCl. Now when you express molarity, you want to put it as a capital M, and then you want to put what the solute is. So you want to specify it as 0.077 molarity NaCl. In the next one, it says many textbooks state the molarity of a substance equals the molality of a solution composed of water. Find the temperature at which this is true. So what the textbook is saying is that molarity is equal to molality as long as the solvent is water. So if you were to look at this, let's look at the expression. The first one is we have number of moles equals number of moles. The one on the left, molarity, is divided by 1 liter. The one on the right is divided by 1 kilogram. So you can say that these two things are equal because the number of moles is going to be the same, so that's going to cross out. The only thing that differs between the two is kilograms and liters. So what you can say is if 1 kilogram equals 1 liter, then that's a true statement. Now generally speaking, we would say that this is for the most part true. So you would say 1 kilogram is really 1,000 grams, and we would say 1,000 grams is 1 liter, and that is a correct assumption for the most part. But if you were to look at it on exact terms, the density of water actually varies with temperature. So if you were to look at it like this, you see a pretty dramatic drop off in the density. Now, when I say pretty dramatic drop off, it goes from 999.5 to 999.95. So it is a very, very, very small discrepancy, but it is there. So if we're looking for this, we need to use the graph to find where 1,000 grams equals 1 liter, and there is no point at which that is true. So if you were to look at it on exact nature, you would say that the molarity of water, or the molarity of a solution with water, is never equal to the molality. Next it says how many grams of copper sulfate are there in 250 mils of 0.25 molar copper sulfate. So we always start off with what we know. We know that I have 0.25 molar copper sulfate. Now remember, the definition of this is 0.25 moles of copper sulfate divided by 1 liter of solution. Now, I don't have a liter of solution, so I don't have 0.25 moles. Instead, what I do is I go ahead and multiply it by the volume that I do have, which is 250 mils. Now, I don't have milliliters here, so I've got to convert first. I would say 1 liter is equal to 1,000 mils, and then I would say 250 mils, and that would now give me my my number of moles. If you were to look and multiply this out, you would get your number of moles to be 0.0625 moles of copper sulfate. Now that's how many moles of copper sulfate I need to add to the water, but I don't want it in the number of moles, I want it in the number of grams. So the next thing that I have to do is I have to say, okay, well, 0.0625 moles of copper sulfate, and now we can go ahead and do our dimensional analysis and convert it to grams. I would say that 1 mole of copper sulfate, and then I would have to do the molar mass of copper sulfate, where there's 1 copper, 1 sulfur, and 4 oxygens. Whenever you find the molar mass, it ends up being about 159.6 grams in 1 mole. Now you can multiply this out, and when you do, you end up with about 9.975 grams, but that's too many significant figures if you were to look at it. The most number of significant figures I have is 2, so I need to take this and I would round it where there's 2 significant figures, and that would be 10 grams. Okay, so you would need to add 10 grams of copper sulfate to 250 mils of water to meet this concentration. The next one, it says the maximum amount of lead the EPA allows in drinking water is 0.015 parts per million. Express this value in molarity and molality. So the first thing we want to do is we got to be able to convert this. So we know parts per million is equal to mass of, in this case, lead divided by the mass of water. Okay, so we know that generally speaking these are both going to be in grams, both be in kilograms. So let's go ahead and take a look at it from that perspective. I want to say, okay, I got to multiply this by 10 to the 6th, sorry, because it's parts per million. So the first thing I'm going to do is I'm going to make an assumption. I'm going to assume that I have 1 kilogram of water. The reason why I can do that is the parts per million concentration is a value of concentration. It doesn't change no matter how much I put in there. So if I have 1 liter or 10 liters or 50 kilograms, it's still the same concentration. So I'm going to put 1 in there, and then I can plug my value in for parts per million. Okay, at this point, you have the mass of water, the parts per million, and you can go ahead and solve for the mass of lead. So let's go ahead and do that. Whenever we do that, you have 0.015 equals, we're just going to leave it as m divided by 1 times 10 to the 6th. Okay, whenever you do this, you get a very, very small value for lead, which we would hope we would have in our drinking water, a very small value of 1.5 times 10 to the minus 8th. Now realize, because this was in kilograms, this value is in kilograms as well. So you have 1.5 times 10 to the minus 8th kilograms of lead. Now you need to be able to figure out, okay, well, 1.5 times 10 to the 8th, negative 8th kilograms of lead, and that is in 1 kilogram of water. So now if I want to figure out the molarity, or excuse me, the molality, the first thing that I can do is I can say, okay, well, 1 kilogram of lead is 1,000 grams of lead. Okay, and then I can say, okay, well, I could look up lead on my periodic table, and when I do, lead is 207.2 grams of lead is in 1 mole of lead. So if you were to stop right here, you would have moles of lead divided by kilograms of water, which is your molarity. So whenever you take this and plug it in your calculator, you end up getting 7.2 times 10 to the minus eighth molality of lead. Now, you can't really express the molarity without the temperature values, but what you can say is, based on significant figures, of which I only have two, the molarity and the molality are going to be the same. Because remember, the difference between the two was 0.9999 and 0.9995. So it ends up being such an incredibly small difference that a lot of times we do express the molarity and the molality as the same values, as long as there's not a wide variation in temperature. Next, in order to create a solution in the lab, you should know that you have to use the molarity equation to determine the number of moles necessary. So here's the molarity that I want. Molarity is equal to moles divided by liters. Now when you're in the lab, you know you have to make a certain volume of solution in order to make it work. And you know what molarity you want, so that allows you to calculate the number of moles. Once you have the number of moles, you have to calculate the mass required by saying, okay, well now I have the moles, and I can go from moles to grams using the molar mass. Okay, once you've done that, now what you're supposed to do, and this is the key part to a solution, is you want to take a volumetric flask, which is this thing right here, and you want to put the solute in, sometimes dissolved in a little bit of water, just to get it going. And then you want to put it in here, and so the solute is dissolved in the water here, and then you slowly add water up to here where it is a total value of 100 mils. Okay, you don't add 100 mils to the solute. So in other words, you don't take out 50 grams of salt and then add 100 mils of water to it, because the powder itself has some volume. The solid has volume. So whenever you do that, you would actually end up over the total volume. So remember, you have a total volume of 100 mils here. You're not adding 100 mils of water. So this one says, how many grams of ammonium phosphate are required to produce 2 liters of solution? So the first thing we do is we say, okay, I've got 2.5 moles per liter, and I know I need 2 liters. So that will give me a total of 5.0 moles, and that is ammonium phosphate. So now I would use the molar mass of ammonium phosphate. I would say 1 mole of ammonium phosphate, I'm going to run out of room here, would be equal to, and then I would have to calculate the molar mass. Whenever you calculate the molar mass, you end up getting a value of about 149.1 grams. And so when you do this, you multiply it out, you get 745.5 grams. Now you have to take into account significant figures. There are only 2 significant figures in both of these values right here, so this should really only be two significant figures, so we'd round it, and it'd be about 750. We don't want to put that dot there. 750 grams. So these two are significant, and that 0 is a placeholder. In the last example, it says a student needs to make 500 mils of 0.1 molar copper 2 solution, where we have an ion. The only substance available is copper 2 sulfate. Give specific directions on how the student can accomplish the task. So the first thing is the student needs to calculate the number of moles. And here's how they would do that. They would say 0.1 times 0.5. The reason why is 500 mils is 0.5 liters. The molarity times the volume would equal the number of moles. So at this point I would get 0.05 moles of copper. The next thing I need to do is I would need to convert the mass. Now, copper sulfate is an ionic substance. It's an ionic substance. So what happens is whenever you put it in water, it becomes copper 2 plus SO4 2 minus. So when I do this, I will have copper ions. So that's what I'm going to do is I'm going to find 0.05 moles And I can't just use the mass of copper. I have to use the mass of copper sulfate, which is where it comes from. So the mass of copper sulfate ends up being about 159.6 grams. So we multiply that by the number of moles we need, and we need about 8 grams of copper sulfate. So now we know how much we need to do. So we've done the calculations, and so the first thing that I would do is I would find the mass of 8 grams of copper sulfate. Then what I would do is I would add about 100 mils of water, and then I would heat it. I would heat and stir. When you do this, the copper sulfate crystals will begin to dissolve in the water. This is not the solution that you actually want. This is just to get the crystals dissolved so now you can do your dilution. Once I've done this, I've got 8 grams of copper sulfate dissolved in 100 mils. The next thing I need to do is I would take a 500 ml volumetric flask. Okay, you take the 500 ml volumetric flask, and then what you would do is you would add the copper sulfate solution that we've already made, and then I would fill it with distilled water to the point where it got to the 500 ml mark. Once I did that, I would have a total volume of 500 mils, and I would have all 8 grams of copper sulfate in it.